circuits. Now, good thing about transistors, the FETs, is that they are ideal switches. Either they are on or they are off. So they can easily model. And even though that is sort of more electrical engineering, that is still nicely described logically, and you will find them in computer architecture books, even the ones that are used in computer science. So next time we are going to analyze some simple examples, things at the transistor level, and we will assume opens and shorts, and we will see what kind of behavior we have. And we will find that in many cases, not all, the behavior is described by a stuck at 0, stuck at 1 model, but there are some cases where it is not. So we will going to see that next time. And after that, next time we are going to start looking at, oh, and I guess maybe I should mention an interesting observation about bridging faults when two lines are shorted. It turns out that detecting those faults is rather easy, and I will mention why. And then we are going to go to the problem of test generation. The test generation is a rather significant challenge. We will look at the approaches starting next time. So you have all been able to access REMCT. So you can work on the assignment and submit it using REMCT. And that is about the redundancy examples. So I will see you next time.
Excuse me, Dr. Malaiya, the class will finish 45, so we still have 10 minutes.
Oh, we still have 10 minutes?
Or 15, 25 minutes.
Oh, okay. So that we don't have to, oh, sorry about that.
Right?
We have 25.
Yes.
Okay, so, okay. So I thought this was a short class. Okay, so we still have some time. And, okay, so let's start with, so let's look at transistor level fault modeling. And now before we do transistor level fault modeling, here is an overview of the MOS transistors, metal oxide semiconductor transistors, which are the better kind. Now there have been a few innovations in related to computers that have significantly changed things. An invention of these transistors is one of them, because before these transistors, the computers, first they built computers using relays, the electromechanical devices. So the relays would either connect or not connect. And then they came up with the cubes, and then they came up with the transistors. So you can have two types of transistors. So one type of transistors are called N-channel, and which we are going to represent in this way. So basically you have three nodes of a transistor. And if the three, so basically the current goes from here to here. So current flows from higher voltages to lower voltages. Well, that's what the electrical engineers claim. It actually goes in the other direction, because the electrons that are flowing. But historically that has been the convention, so we just follow the convention. So it goes from higher voltage to lower voltage. And here is the controlling node, which is called a gate, which is kind of confusing because we use the word gate to also refer to the logical gate. But this basically means if you apply a 0, then there is no channel here, and that means the two nodes are basically not connected. So that means they are open. And for an n-channel transistor, if input is 1, a channel is induced, and that means you have the switch is closed, like this. And for a p-channel transistor, here's how we are going to draw. Now this means that this is a p-channel transistor. If this is a 0, then this means this is closed. So because there is a channel between here and here, and if situation is like this, then there is no channel, so it is open. Now let us assume the transistor. Okay, let me first show you an example of a gate using these transistors. And as an example, let's look at the CMOS NOR gate. Now, many computer scientists would not have seen this diagram, but if you look at our CS530 textbook, there is a discussion of transistor level implementation of some of the gates. That's a book written by Pat and Patel. And also, you can find this stuff on the web. So here's the CMOS NOR gate. So basically, a gate has the three important nodes. You have the high, and you have the low, which is also called the ground. So high is, well, what depends on the technology. It could be, I don't know, 1.5, 1.7 volts, whatever is the status. So whatever is the higher voltage. And here is the output. And basically, a gate works on the principle that depending on the controlling lines here, output is either connected to high or it is connected to low. So here is the NOR gate. So you have two p-channel transistors. And let's call the inputs A and B. And then you have two n-channel transistors. Oh, I'm sorry. N-channel transistors. And this is the B. This is the A input. And here is the B input. And let us try what will happen if A is equal to 1 and B is equal to 0. Now you can see this here. And notice that since this is a p-type of transistor, so this transistor is going to be open. And this is also a p-type of transistor. So this is going to be closed. Notice here, between these two nodes, there is no direct path. This is connected here, but this is not connected. So there is no direct path to high. Okay, does this have a direct path to low? Let's find out. Now notice that since this is 0 and this is a N channel, so this is closed, this is open, and this here is closed. By closed, another term for closed is on, that means it is conducting. So because this is 1 and this is N channel, so you have a channel here. So basically here, notice that you have a direct connection. This switch is closed here. So output in this case is going to be 0. Or in other words, low. And similarly, you can verify the operation for other cases. And of course, as you know that for a NOR gate, if you have a NOR gate, then the output for a NOR gate, the output is 1 only in this case. And you can verify that this is indeed a NOR gate. So basically what we have done is, here's our NOR gate. And we have applied a 1 here and a 0 here. And obviously, if this was an OR gate, this would be 1. But because of this inversion, that's a 0. And of course, that is this case right here. So this is how, and notice that this is a complementary MOS. So you have two complementary structures. So whatever structure you have here, you have exactly complementary structure here. So if these two are in series, and they will be in parallel, and so on. And that's why this is called CMOS. And incidentally, notice here that in a CMOS circuit, either you will not have a direct connection between high and this, or you will not have a direct connection between this and this. So output is at a given time either connected to high or low, but not both at the same time. Except when there is switching, except when there is a transition going on. So whenever a CMOS gate is not switching, it will consume no power because there's no current flowing through it. But of course, some of you know more details, so there actually would be some kind of leakage current, which is a very small amount of current. But no significant current would be flowing, except during switching. And that makes CMOS especially good for high density, because you can put a lot of components there, and as long as they are not switching, it's going to consume very little power. The power consumption would be basically linearly proportional to the number of nodes switching in a CMOS circuit. Okay, and now look at let's look at the switch level fault modeling, and let's do that here. And anyone knows how to fix those clocks? The
Battery?
clock we had in the back?
I think it's our battery.
Probably.
Needs a battery, it's not moving.
Oh, so it's a battery?
I think.
Oh, it's not connected to. So that should be easy then. Maybe I'll try fixing it. And see, it seems to be running, right?
It's not.
No, it's not.
Oh, it's not running.
It needs
Oh,
a battery.
maybe it needs a battery.
Yes.
Oh, I see. So I guess it's right only once in a day. So, okay.